topic today is to share my modeling methodologies in the current ongoing studies about a decision-making test with EEG to shed some light for future studies instead of quantitative results. So let's start with leisure and work. Every day in our life, our time can be divided into leisure and work, and they can be evaluated in terms of instrumental value, intrinsic value, and perceived effort. And generally, they are contrasting each other in terms of these axes. And the key idea here is that suboptimal or imbalanced allocation decision can often lead to problematic or maladaptive behavior such as addiction, procrastination, etc. So in order to study these kind of phenomena in terms of time allocation, we have some problems and challenges. First is, how can we design an experiment to operationalize it into a decision-making task? The second is, how can we set up EEG to help us gather insights during the activities? Then, how can we measure the subjective experience about these three axes? And then, what about other latent or unconscious motivational drives that is not captured by these three axes? And there is a problem about these subjective feelings can change over time or have a learning effect. And the last one is the most important one is, how can we develop a computational method that help analyze these three types of data in a cohesive manner? So for the experimental design part, we have the evaluation stage for 1 minute and allocation stage for 5 minutes, and these two repeats for 18 trials. And for the allocation stage, we have three options of time allocation. The red one represents work, and we use B5 inventory 2, and leisure we use digital media use, which is the blue block. And the three options represent the three levels of procrastination tendency, namely low, neutral, and high. Then we use a switch continuum mechanism to choose between these three options, which is after the first leisure block, we let them choose whether to switch to the work block or to continue leisure. If they choose to continue, they'll left with B or C, and then they can choose it again after the next block is finished. If they want to switch, they will switch to B. If they don't, they'll go to C. So we call these switch continue points the decision points, which we mark by EEG event markers. For the quantification part, our interface looks like this, and you can see for each option we have two questions regarding value and effort, and we completely redesigned the scale for this experiment. The traditional scales have some problem, which is that for lower points, they have insufficient precision, and for higher points or visual analog scale, they can be difficult to answer. So our interactive longitudinal scale uses these 0 to 100% range, and use a gradient to represent a distribution with a cutoff of 2 sigma to help the participant to answer a 99% confidence interval for both questions. So we can then use these to get a belief distribution and because this is logic normal, we plug it in logic function to get a normal variable, and then we can plug it into a entropic risk measure to get a fixed value instead of a distribution. This risk measure is very canonical in economics, and it allows us to estimate a optimistic bias or pessimistic bias in the long run. Now, for the big part, which is the inference part, we have the we can first look at a naive model which looks like this. You just predict the ABC three choice, each with their own value and effort and plus an intercept. But this has a problem, which is that if we use per trial inference, if the actual data chooses one option, then the predicting U will be simply infinity, and the other will be negative infinity, which blows up. So we cannot do that. And there is a property of softback shift invariance. So this means that alpha cannot have three separate identifiable alpha. This leads us to the model 2, which looks like this. We can set the option B as a baseline with 0, and we can subtract B from the other two, and then we'll get this one. But this is still per trial inference, and if it happens to get a negative beta, it is uninterpretable because we cannot, higher value usually means higher probability of choosing that. And there's also too many parameters, potential issue of confounding. So our model is, actual model looks like this. So we use a single alpha for both directions with opposite sign, and a single beta for a combined composite value connected with a kappa as a trade-off sensitivity. And we're doing this because we want these to live in real numbers, and this allows us to put a state space model onto these parameters to gain the leverage of time series data. And this is just a simple AR1 dynamics. And we can use Kalman filter and treat Y as noise observation with Fourier gamma augmentation to do Kalman filter inference. So initial result is that you can see this is the predicting probability. There's still plenty of room for EEG. And EEG modeling looks like this. So, yeah, I don't have time, but we can see we can plug EEG into the switch continuous choice here, which completes the whole model. Thank you.
All right, so we have time for questions. Any questions from the reviewer? Okay, yes.
Which kind of the EEG feature you will use for your model?
We will use power bands.
Just power band?
Because power bands is used to collect the activity-wise over the period, and also possibly we can incorporate drift diffusion model into this during the decision point when they choose to switch or continue. That's also implementable.
Yeah, because for your design, maybe you can consider that maybe use the entropy or something for this one. Especially so because not only the power band power spectrum, but actually maybe you can use the connectivity to know more about this one.
Yeah.
Actually, so you can input any
it can
features
be any
into it.
feature
Yeah.
to put it into. Yeah.
So do you already have the data you show EEG is that from how many subjects do you have?
No, this is not EEG. This is just using value and effort to predict. So this is to show that there's room for EEG features to put in, because this does not really have our score quite
So
low.
when you carry out the analysis, all of this model, you will test them like with the individual EEG, or I mean, for each different person, they will have different models that's best fitting the result, or
We can use a hierarchical Bayesian model to collect the parameters.